not seeing Pedro. Fatima, there you are. Aileen. Eileen. I knew I was doing it wrong. Cindy. There you go. Caleb. There you are. Caitlin. There you are. And Justin. So we're missing Justin. All right. So over here on the Tonkawa side, I've got, is it Jasmine? Okay. Emily. I'm not seeing Emily this morning. Chase?
Yep.
Okay. Monica, you're here. Karis? All right. Miracle? Here. You're hiding. There you are. Megan? All right. Hannah? Braylon? And where's Veronica? Has anybody seen Veronica yet this semester?
She was gone in one of my classes yesterday.
Okay. I wonder if she's just running a little late. Okay, so we got everybody. All right, there are some differences this semester. So let's talk about the major difference in how I run this class over how I ran General Physics 1, because most of you are in my General Physics 1 class. Major difference is General Physics 1, no matter what I could do, you were going to have a comprehensive final. It just was the nature of the beast, okay? General Physics 2 is very different. We start with electricity. Actually, we're going to start with waves. We're going to do simple harmonic motion. That's what we're starting with today. We will start, after we get waves and mechanical waves, we'll go into electricity. Then we'll go into magnetism. Then we'll go into optics. The way Physics 2 works is it's very conceptual, a lot more for you guys, and I teach it very different between my engineering physics class and my general physics class. When we're with mechanics, you kind of teach it all the same. But one of the things that I do is that you will not have a comprehensive exam this semester. It's just a little weird and a little unfair to do radically different topics and then try to slam them all back together at the end of the semester. You will still have a quiz that I have for assessment, a non-droppable quiz, and that will be comprehensive. It'll have concepts from all throughout the semester, but the final exam is only going to be over optics. So when we get to the optics section, the final exam is only over optics. I try to fit in 5 exams, but depending on how the semester goes, it may only be 4 exams. Usually you'll get an exam about mechanical waves fairly quickly, and then just how it works out, whether or not I can fit in 4 exams or 4 exams for the electricity and magnetism stuff. So it's just going to be a little bit different as to how this class kind of works out. There will be 1 exam in the semester that half of it's in class, half of it's take home, because it's just totally unfair to give an exam on that, because if you start that problem the wrong way, you're toast. So there is an exam in the semester that's partially take-home exam. I still will do lots of quizzes, so you'll have lots of quizzes throughout the semester, and some quizzes may be in class this time, but if it's an in-class quiz, it'll maybe only 1 or 2 questions, okay? Just kind of giving you a heads up on that. So I do this class very differently than I teach the other one, partially because the concepts are different. Syllabus, this is, there's your WebAssign class key. Hopefully, I got all the right buttons pushed, and you can log right into WebAssign. I would like for you all to get into WebAssign, do that getting started WebAssign exam real quick, get that going, and make sure that we don't have the problems that we had last semester. Luckily, all of the login problems, those were a different set of problems, but I want to make sure I have all the buttons clicked appropriately. And if anybody, if it asks for, if you're in the trial subscription, holler at me, because that means I didn't do something right. Because you all should be direct billed or whatever for this semester. So they're working all that pieces out. Syllabus, same kind of thing. Reminder, I do not take late work. It's not gonna happen, okay? If you think you're gonna miss something due to, because this is you guys' graduating semester for most of you, There are things that you will have to be doing. So if you know you're out on transfer day and that's a day that the homework's due, get a hold of me ahead of time and we can make arrangements. I will not make arrangements post time, okay? I won't be doing that. And as I'm sure you guys have heard, we've had some new requirements on what gets posted on Blackboard, how it gets posted on Blackboard. So if you have not dealt with your note-taking skills, I suggest you should start rushing up on them because there'll be a lot of folks that aren't posting their notes anymore, just because of the various requirements that we've got to jump through hoops and get there. My notes, if it's a PowerPoint, I try to post the PowerPoints. I kind of go back and forth, and I do have links on there. You will notice that there is a change in the grading scale. It's not the overall grading scale. It's still 87.5 to 100, but homework is only going to be worth 30% of the grade. Quizzes are going to be worth 20% of the grade. But most of your quizzes are going to be take-home type quizzes, so it shouldn't be too bad. But the homework and quizzes are still going to be worth 50%. It's just a little bit different. You will also notice. Do what, ma'am?
We're not saying the computer.
Oh.
We need somebody like him.
Okay, hang on. Thanks.
Justin is here.
Okay, Justin's here. Okay.
Yes.
There. Now let's see.
Okay, perfect.
All right, let's see. Get there. There we go. How's that?
Yes.
All right. All right, sorry about that. So the grading scale is a little different. You will also know that homework, even though last semester, if you did your homework early, it was worth 25% bonus credit. It's only worth 10% bonus credit this semester. But it's still bonus credit, right? It's still bonus credit. And you're also going to find one of the things that I am changing and I'm trying to do this semester is I'm trying to do a few more fun type assignments, and you're going to get your first one today, so you'll see it. So there's a lot of opportunity to get easy points, all right? A lot of opportunity to get easy points, but just be aware that homework's, it's not 25% this time. The final exam is going to be on Wednesday, so we're all doomed. We got to be here Wednesday at 8 o'clock, same kind of situation as we had before. Okay, so, no, I want to go back. All right, I did it 2 places, okay. All right, there's the link to WebAssign. So it does go direct through. So I'm going to flip back over there real quick, and that means I got to come back to Blackboard, but that's all right. That's my General Physics 1. There's General Physics 2. There we are. So what you have right now is the getting started one is due on Friday. Just make sure everybody's been able to log into WebAssign. And the sound pre-work is due on Friday. Mechanical waves, we're going to start looking at sound. And then our homework for that chapter is due, 29th. So we've got some time to get that homework in, and we're going to be doing quite a bit. So, and I'm also going to be doing some virtual labs as part of this in WebAssign. That's why I left this one up and open. So there's going to be some more fun, kind of interactive type things to help you guys out with various things. So hopefully that will help you. Let's see if I can go back. See if it let me go back. So that's the grading scale, the pieces. Under course materials, you guys should have access to your ebook, but also what I have done is I have linked and given it to you as another text. This is OpenStax. It's completely free. All you have to do is go in and click, but it gives you another textbook to look at. It may be a little easier, or it may explain things a little differently, that have different examples. So hopefully that will help you out as well. So it's just another resource for you. And as I have individual resources, they will pop up. So let's kind of start. Any questions about the differences or syllabus things or that you guys have? Oh, it's Wednesday morning, first semester, first day of the big classes, right? All right, so let's talk. There's your web. I've posted the WebAssign key in a number of places, hoping that it will all work out. So this is your first assignment. It's kind of a fun assignment. I want you to find, and we're going to start talking about simple harmonic motion. I want you to find an example of simple harmonic motion. Clock, pendulum, and I'll show you one here in a second, a valve stem, those are all examples of simple harmonic motion. It's a repeated pattern, and we're going to start talking about that here in a little bit. It's worth 50 points, 20 points for the video, and I want creative videos. I don't want a clock pendulum. I'm going to show you a clock pendulum that's not even your simple clock pendulum. So you can't necessarily use that. The valve stem is not going to be allowed either, okay? The valve stem's not going to be allowed either. You will need to explain how your video exemplifies simple harmonic motion, and then you're going to be able to write the wave equation. And we'll probably introduce the wave equation on Friday. You'll notice that this one is due on the 26th, okay? So you'll have plenty of time to get the wave equation and plenty of time to ask questions. And if you're not sure, I'm going to count your video. You can ask me, all right? So you're going to get 20 points for the video, 10 points for your explanation, and 20 points for your wave equation. So let me give you an example. So here is an example. Let's see if I can put it. We'll play it. That, I'm going to mute that. It doesn't need it. This is my cow clock in my office. So for those of you who haven't been in my office lately, you'll notice that my office has expanded. Well, the space in my office has greatly diminished because my office has greatly expanded the contents of my office. One of which is my cow clock. We run a micro dairy, and so we have Holstein cows. We also have Midlothian Shorthorns. So the pendulum is one example of simple harmonic motion. It has a complete cycle. It goes back and forth. But there are 3 other examples of simple harmonic motion on my clock. My clock has an example of the second hand going around. It's going to complete a complete cycle. And we're going to get a wave equation by going around the circle. So if my second hand is an example of simple harmonic motion, so is my hour hand, and so is my minute hand, just that the period, the time it takes to make a complete cycle, the time that it makes a complete cycle is going to be different. So I do get a different timing for my clock. So a clock, this kind of a clock, the tongue's going back and forth. It has a top, it has an amplitude, how far the tongue swings, my amplitude of my circle, how far the maximum distance that it gets, will all be examples of simple harmonic motion. So you got a fairly easy 50-point assignment that you can do that be a little bit creative as to what simple harmonic motion is. So that's one of the assignments that's going to get going. So hopefully that will make it clear. Now, you can either upload your video to Blackboard or you can email me your video, all right? So you can either upload the thing to Blackboard or email me. The other thing is, I've also done some things in Blackboard to hopefully make things easier. There's my email. You can click directly through Blackboard and send me my email, or send an email. I will warn new folks, as some of you already know, trying to check my email in 3 different places is a real pain. So if you have a question in WebAssign, email me directly. Don't try to have WebAssign email me because I may or may not see it out of WebAssign. It's just one of those things. When you have so many places to check emails, it has a tendency to get lost. But feel free to email me. And most of you know I'm pretty good about responding within 24 hours about emails. So, and weekends I should be a little bit better than I was before. So hopefully that will help. All right, so now we're going to get started kind of diving into things. Okay. All right, I'm going to switch to switch to the document cam, let's see if it'll all work. Yeah, it does work. All right. Now we gotta get stuff straight. And then we get to play with cameras. At least in this room, I've actually moved cameras around. I was in a different room last time, so we'll see what we can get. All right. So from Physics 1, hopefully most of you remember Hooke's Law. Okay? And this is where we're going to start out. Let's get that focused a little bit. Hooke's Law, we said that that was equal to the force was equal to negative kx, where k was my spring constant and x was the distance or the stretch. Okay? And we did a problem like that, and I've actually brought it out. I brought the example here, so if I have something that's hooked, there's my spring, and this was my initial x, and if we put a weight on it, mass times gravity was our weight, and we would get a stretch in the spring. And there would be a little difference here, and then we could calculate the force, and that was equal to minus kx. And I think you even, if you took your final in my class, you even had a Hooke's Law problem on the final, right? So we all know how to calculate the spring constant. The spring constant is going to be the force divided by x. This is going to be the magnitude of the spring constant. And we can actually do that. So now we're going to do one, just to get us started here. Let's see if I can do this. All right. This is the fun part. Teacher camera. Okay, there we go. And now I want to zoom the camera. So let me do that. Okay, there. Okay, I want to come. It's going to take a second here. There we go. There we go. See if I can present. So we have it. Nope. Well, let me do that. See, over here. All right. So there we got the camera. Maybe. All right. So you folks over in Enid, do you see the spring and a Kleenex box?
We do not, we're seeing half of you where we were. There we go.
There's my hand?
Classroom. No, we're not seeing the doc cam.
No, I'm not the dot cam. I want you to be seeing the spring and the Kleenex box.
Yes.
Okay.
That's what we're seeing.
All right.
Sorry.
That's okay. Got the spring and the Kleenex box. All right. So remember when we did the Hooke's Law? Hooke's Law, we started out with measuring the spring. The challenge of not being in the same room with my physics lab is that trying to do demonstrations is always fun. So I had to go get a ruler. So I got a ruler, and we can actually measure this. And this ruler's a little tough to actually see. But if I measured the spring, and I actually did it, the spring actually measured 3.9 centimeters before I put a weight on it, okay? So it actually measured 3.9 centimeters. I have my handy dandy. I did manage to bring out my handy dandy calculator, so life is good. So I got that part. I'm going to put on. Let's see, I forget what this one is. Well, I brought a 200-gram weight, so I'm going to put a 200-gram weight, and we're going to get a stretch. Okay, so we got our 200-gram weight. So if I do my mass times gravity, it's going to be 0.2 kilograms times 9.8 meters per second squared is going to give me 1.96 kilograms meters per second squared, which gives me 1.96 newtons. So I've got that. Now I got to measure the stretch again. So I'm going to measure my stretch. So now I've got 10.8 centimeters. So 10.8 centimeters minus 3.9 centimeters gives me 6.9 centimeters. But I can leave it that way if I want to calculate my spring constant. I can leave it that way, but if I want to put it in meters, I've got to divide by 10. I might get my 0.69 meters. So my force divided by x is going to give me the magnitude of my spring constant. So 1.96 newtons divided by 0.6. Nope, that's not right. 0.069. It's the beginning of the semester. So if I do that, 1.96 divided by 0.069 is going to give me my spring constant of 28.4 Newton meters. Now, when we start diving into what we're going to call the wave equation associated with my spring, we're going to need, did I do the dot? I didn't do the dot cam? I didn't. You guys are going to have to holler at me. So there's the calculation that we have. So we've got our 2.8 or 28.4 Newton meters for our spring. But when we start doing the wave equation associated with our spring, we're going to need to know what the spring constant is. Because if I have a stiffer spring, it's going to behave differently when I set it into motion. We're actually going to set this situation into motion. It's going to behave a little differently. So let's go back to the teacher cam here. There we go. So when I set this into motion, we know what it's going to do, right? If I drop this down, it's going to bounce up and down, and it's going to continue to bounce up and down, and that's an example of simple harmonic motion. It's just going to stay in that same state where it's bouncing up and down into the system until gravity or until air resistance finally gets it to stop. Because it eventually will stop due to air resistance because we don't necessarily have absolutely perfect thermodynamics says we're going to lose it. We're going to lose some of that energy due to heat and friction, and we can't have a perpetual motion machine. So it's just going to bounce up and down. Now, mathematically, when we represent that piece, we're going to represent it as a wave. And let's look at how that wave gets represented. So let's go back to the document again. This is always the challenge. This is why a lot of people don't want to try this. So if I'm looking at the spring and it's bouncing up and down, it actually has a midpoint here, right? It has a midpoint. This is going to be referred to as the amplitude. How high or how low it goes above that midpoint is our amplitude. If I were to put a pin on our spring as it bounces back and forward, and I'm dragging the piece of paper, we know that it's going to draw, the kind of the function that it's going to draw is going to look like this. Okay? It's going to go up and it's going to come down. It's going to go up and it's going to come down. And if I had a chart recorder and I had a pin on the bottom of the mast, that's exactly what we would see. Which means if I put my midpoint in through here, this represents the amplitude. And we're going to use the big letter A to represent the amplitude when we start looking at those pieces. We're gonna need the spring constant down the road, but we're gonna start looking at the wave and how we're looking at the piece. From here to here on our wave, this is a cycle. That's one cycle. From the same point or an identical point is one cycle. So I can have a cycle here. I can have a cycle here. Any place that I'm going from one point to the next, I'm going to have a cycle. The time that it takes to do that cycle is the period. We're going to use the capital letter T, and that represents the period. So if this is a time graph, that's what I'm going to get. Now, if this is a distance graph, the distance from here to here, so if this is distance, that distance is one wavelength. So, and we're going to use the Greek letter lambda for wavelength. So if I'm doing distance from here to here, that's one wavelength. If I'm doing time, that's my cycle, and my cycle is a period. Somewhere along the line, we talked about frequency. And frequency would be like the number of cycles per period of time, right? So if I'm looking at different things, I'm going to get the number of cycles per unit of time, or I'm going to get frequency is 1 over capital T, or my period. So if I'm looking at my units, this is 1 over seconds, and that's going to give me a unit of what we call hertz. Okay, 1 over seconds is our unit of hertz, and frequency is inversely related to the period. So that's going to so I'm going to have a diagram at some point, and be prepared to label a diagram, and I will tell you that I will have somebody at some point in time tell me that whole distance right there is the amplitude. That's not correct. The amplitude is that separation from the midpoint up. Okay? So I've got my frequency is 1 over the period, my cycle relates back to the period or the frequency, the number of cycles per time, and my distance is wavelength. So now let's look at this lovely piece here. So I have something that looks like this. You guys have seen this function before. You've seen it in math class. And that function before is what? If I'm going to write that mathematically, what am I going to write? Got somebody who tells me that they're going to write the sine of something. Is it just the sine?
Would be what y equals.
Well, y equals, but that's going to be related to the amplitude. But sine is one way to represent it. Is there another one out there?
Oh, cosine.
Yeah. Okay? Sine or cosine can represent that particular function. The only difference between the sine and the cosine representing that particular function is where I start. Okay? It's absolutely where I start. Because what happens to us, sure I've got to bring it in my notes. Okay. If I use the sine of the angle and these, and we'll go back into your pen or your appendix and look at it. If I do it in terms of degrees, sine is equal to the cosine, or the cosine is equal to the sine. And they're just off by 90 degrees, okay? So I could describe that function either as a cosine function, or I can describe it as a sine function. And I'm bringing this out to you because your book is going to do it one way, and the lab is going to do it another, all right? The only difference is where I choose to put my zero, okay? The only difference is where I choose to put my zero. Because I have that relationship between sine and cosine. There is a mathematical relationship between sine and cosine. So, if I'm representing this one, we can write an equation for our system. And this time we're gonna look at the x direction, okay? We're gonna look at how this goes. And if I have a little particle that's traveling like this, where it goes down the system, I can be looking at how far in this direction it's traveling. And if I look at that, we can write it as x is equal to a, where a is my amplitude, okay? A is my amplitude, cosine, and that's how our book does it, cosine, and we're gonna use omega right there. And we're gonna do this times time. So we're looking at the motion of a particle along this wave in the x direction as with respect to time. And this omega is going to be referred to as our angular speed, and we've seen this before, right? We've seen this before. That's our angular speed. Because if I do this, okay, if I do this, and let's look at a circle. So I've got a particle on a circle, so here's my cross section, and now I have something that's moving around the circle, and I've got my little chart recorder. Guess what happens? If I'm looking at where it is on the x-axis, I'm looking at how this is traveling, and here's my amplitude. That's the biggest amplitude it'll be. This is the smallest it'll be on the other side. And I'll look at how it's traveling back and forth along that circle just on the x-axis. So I can relate it back to circular motion. So I can relate it back to that angular speed that I had before. And we saw that before. My angular speed is going to be my change in angle with respect to my change in time. And we've seen this before, that could also be 2 pi if I'm looking at my circle. 2 pi being the radians of my circle, and t being my period, which means that this can also be 2 pi times the frequency. Okay? So we'll be able to go back and forth. Now, you can go in and look at it. I could sit here and derive it for you, but you're all going to go, okay, and gloss over. So what I'm going to do is do it this way. We also can find out that this happens. That our angular speed, 2 pi times the frequency, is also equal to, in my spring system, the spring constant divided by the mass. So I end up having to go back to that spring constant, so my spring system really helps me deal with simple harmonic motion. And helps me deal with where my motion is, and we're looking at how we're going to transfer and get those pieces back and forth. So when you guys go to lab, all right, when you guys are actually in lab and you're actually going to do your lab, what you're going to do in that lab is you're going to do this. You're going to take that spring. First thing that you're going to want to do is calculate the spring constant, because you're going to need it, all right? And it'll be hanging from the top. And what you're going to have is you're going to have a basket down here. And you'll have a motion detector down here, okay? And if I'm looking at my distance y, it's going to be some distance, my midpoint, this is my y naught, that initial distance away from the motion detector when I'm not swinging or not bouncing. So I'm going to have that. And then you're going to look at this up and down motion related to the cosine omega t. Or in the lab, it'll actually be sine omega t. But remember, whether it's sine or cosine, it doesn't really matter. It just tells me where my starting point is. And you're actually going to be able to get the wave equation. So we will be able to read a wave equation from the graph that you get that goes like this. And we're going to do that on Friday. I'm not going to start having you read wave equations today, get you an opportunity to do lab. At least the Tonkawa side will have lab today. What day is your guys' lab scheduled over in Enid? Did you have it yesterday? Monday. So you guys are going to be a week behind? Okay, we'll get it straight. Not a problem. All right, So I'll see you guys over in Enid on Friday. You guys get ITV on Friday. And we will, and then if you've got questions, holler at me, but definitely get logged into the WebAssign before Friday.